Hello, this is Dr. Michael Hassan, the engineering doctor with Innovate, and this is course titled Digital Logic Design or Digital Systems or Digital Electronics. This is lecture number 1, Number Systems. This is a disclaimer for you to read. References, there are many references in digital logic design. Few of them is Digital Logic Design by M.H. Hassan, Fundamentals of Digital Logic with VHDL Design by Brown Forensic, and Fundamentals of Logic Design by Ruth. And as I said, that you may find many other books on Amazon.com or in your local library. Course contents. Today we'll talk about number systems, we'll talk about binary codes, logic gates, Boolean algebra, analysis and design of combinational networks design using standard modules, arithmetic combinational network design, flip-flops, digital counters and registers, analysis of synchronous sequential networks, design of synchronous sequential networks, and the design of synchronous sequential networks will include 4 steps: derivation of state graphs, reduction of state tables and state graphs, state assignment, and implementation, hardware implementation. So we'll talk about digital system design using ASM charts, and we'll talk about asynchronous sequential networks. Course features a strong emphasis on digital system design and analysis procedures, coverage of number systems, logic devices, and logic technologies, an in-depth coverage to combinational analysis and design, comprehensive coverage to synchronous sequential networks, detailed methodologies to design algorithmic sequential networks, coverage to asynchronous networks analysis and design, emphasis on modular design and standard digital circuit modules, detailed design techniques and examples with VHDL, many chapters. VHDL is treated as an integral part of the course, yet can be left out if not needed. Numerous number of solved practical examples and problems throughout. Number systems. The most popular number system is the decimal number system. It's called decimal because it has 10 digits, 0 to 9, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it has a base, called a radix of 10. Now, any number from any system may have an integer or integral part and may have fraction. It may and it may not. Now, if it has fraction, it separates actually the integer part from the fraction. A decimal point in case of decimal numbers, or a radix in general, the radix point, fraction point. So in this example, we have 6,789.1234. This is a decimal number, and we would like to evaluate this number as a polynomial. Every digit will have a weight. So starting with the radix point, to the left, have the integer number. The least significant digits, which is next to the decimal point or the radix point in general. We have the digit 9. The digit 9 will have a weight. Every digit will have a weight. The weight of 9 is 10, which is the base to the power 0. The weight of 8 is 10 to the power 1. And the digit 7, the digit 8 has a weight of 10 to the power 1. The digit 7 has a weight of 10 to the power 2. And digit 6 has a weight to the power 10 to the power 3. If we start from the radix point to the right, we have 1 has a weight of 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 3, and 10 to the power minus 4. So therefore, this number can be represented as 6 times 10 to the digit multiplied by its weight plus digit times the weight plus digit times the weight, and so on and so forth to the end of the polynomial, as you can see it here. So, in general, any number n could be depicted or represented as integral part plus fractional part. The integral part will be dn times the weight, which is the base, to the power n, and so on until we reach the least significant digit, which is d0 times b to the power 0. Now for the fraction, we'll have d minus 1 times b to the power minus 1, d minus 2 times b to the power minus 2, plus d minus m times b to the power minus m. Or in general, we can represent this polynomial as a series. So capital N, this is the value of the number from I minus m to n, di bi, di bi, b to the power I. Now the binary number system, as the name implies, has two digits, 0 and 1, and a base of 2. The octal number system has 8 digits, 0 to 7, and a base of 8. The hexadecimal number system has 16 digits, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After the 9, we have A, B, C, D, E, and F, where A represents 10 decimal, B represents 11 decimal, C represents 12 decimal, D 13 decimal, E 14 decimal, and F 15 decimal. So the hexadecimal number system has 16 digits and a base equal to 16, and the base equal to 16. So a decimal number between 0 to 15 with base 10 can be represented in any other binary, in any other number system, like the binary number system, base 4, base 6, base 8, and base 12, base 14, base 16, and any other non-decimal system. So 0, for instance, is equivalent to 0, 0, 0, 0 in binary, equivalent to 0 in the number system to base 4, equivalent to 0 in octal, and equivalent to 0 in hexadecimal. Now, as you can see, the binary, it's from 0, 0, 0 to 1, 1. Now, generating this table, it's very easy. If you start with the least significant bit, the bit will toggle from 0 to 1, 1 to 0, then 0, 1, 0, 0, 1, and so on and so forth to the end, till the number 15 decimal. Then we start with the next row, the next significant row, which we have 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and so on to the end. Then we will have 4 zeros, 4 ones, and so on. And we'll have 8 zeros and 8 ones, which we finish this table in the decimal sequence. Now, for the number b is 4, the base is 4, so we have 4 digits in this number system, which is 0, 1, 2, and 3. After 3, number 4, decimal 4 will be represented by 1 0, and so on and so forth. Because 1 0 white is 1 0, because 0 times 4 to the power 0 is 0, plus 1 times 4 to the power 1, which is 4, and they add up based on the polynomial expansion of the power, so we add up to the value of 4. 5 will be 1 1, 6 will be 1 2, and so on and so forth. So we'll get 23, then the 1 3, we don't have 1 4, because 4 is not an accepted digit. Base is a 4th system, so after the 1 3 we'll have 2 0, which is 8. Okay, so this is how we evaluate all the numbers for any base which corresponds to the decimal base is 10. Now, conversion of bases. To convert a number n with a base b1 to another base b2, there are 3 possible cases to consider. Case number 1. b2 is equals to 10. So by using the polynomial, we can convert any number from any base to a decimal number. So in this case, we are converting binary, octal, hexadecimal, other non-decimal number to decimal. So the rule is simple. We express the value of n as a polynomial in terms of b1. The polynomial is evaluated using decimal arithmetic. As an example, we have the binary number 10111.111. So the number to the right of the radix point is the fraction. To the left of the radix point is the integer or the integral portion of the number. Again, the weight actually of 1, the first digit 1, will be 2 to the power 0, which is 1, 2 to the power 1, which is 2, 2 to the power 2, which is 4. The weight for 0 is 8, and the weight for 1 is 16. To the right of the radix point, the weight of the first digit 1 is 2 to the power minus 1, which is 1/2. The weight of the second digit, this one, which is 2 to the power minus 2, which is 1/4. And the weight of this digit, the third digit, will be 2 to the power minus 3, which is 1/8. Because 2 to the power minus 3 is 2 times 2 times 2, which is 8. So 1/8 will be the weight of the last fractional digit 1. So therefore the polynomial will be 1 times 16 plus 0 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1. Then for the fraction, 1 times 1/2 plus 1 times 1/4 plus 1 times 1/8. And if you apply decimal arithmetic, you will end up 23.875 in decimal. So therefore, we say the binary number 0.1 is equal to 23.75 decimal. Another example, this is an octal number. It's very similar actually. It's very easy. In a very similar way, we will have the weight of 0 is 8 to the power 0. The weight of 1 is 8 to the power 1, and the weight of 5 is 8 to the power 2, which is 8 times 8, which is 64. Therefore, actually, and the weight of the fraction 4 be 8 to the power minus 1/8. Therefore, actually, the value of n will be 5 times 8 to the power 2 plus 1 times 8 to the power 0 times 8 to the power 0, and plus 4 times 8 to the power minus 1, which is 328.5 decimal. Therefore, we say the octal 510.4 be equal to 328.5 decimal. Another example, we are expressing the ABC.1d hexadecimal number to the base 16 in decimal. Again, we have A has a weight of 16 to the power 2, B has a weight of 16 to the power 1, C will have a weight of 16 to the power 0, and the 1 we have 16 to the power minus 1, and D will have a weight of 16 to the power minus 2. We replaced A with 10, and B with 11, C with 12, and D with 13, and we do arithmetic calculation. We end up with the number 2748.12812 decimal. Therefore, the hexadecimal ABC.1b is equal to 2748.1132812 decimal. And another example, this number is to the base 12. We'd like to express it in decimal. We have AB 9.12, and we would like to express it in decimal. So we have A times 12 to the power 2, because the weight of A 12 to the power 2, B 12 to the power 1, 12 to the power 0, and 1 is 12 to the power minus 1, and 2 12 to the power minus 2. So we have A times 12 to the power 2, B times 12 to the power 1, 9 times 12 to the power 0, 1 times 12 to the power minus 1, A plus 2 times 12 to the power minus 2, and do simple decimal calculation. That would number 581.09722221 to the base 10. So we say AB 9.2 to the base 12 is equivalent to 581.09722221 to the base 10. Case number 2, when we have neither B1 nor B2 is equal to 10. This is a conversion among binary, octal, hex, and other non-decimal numbers. The rule, each octal digit is represented by a 3-bit binary set, and each hexadecimal digit is represented by a 4-bit binary set. So we start from the fractional point to the left of any binary number, and we convert to hex and octal integral digits. We start from the fractional to the right of any and convert to hex or octal fractional digits. So what we will do, we will group the bits as sets of 3 for octal, as a set of 3 bits for octal, and as a set of 4 bits for hexadecimal. Now, if we needed actually a single bit or a zero at the left-hand side of the number, which is at the integer part, or the right-hand side at the fractional part, it means the most significant bit of the integer part and the least significant bit of the fractional, we can add zeros to complete the set of 3 for octal and the set of 4 hexadecimal. The set of 3 bits for octal, the set of 4 bits for hexadecimal. As an example, we have a binary number which is given here 1010101111000001. We'd like to express it in octal and in hex. We'll take the number, we group it as a group of 3. As we see here, we needed actually an extra 0, we added 0. This will not change the value of the number. So we grouped it, and each group will be converted to its equivalent octal digit. So 101 is 5, 010 is 2, 117, 100 is 4, 0.000 is 0, 117, 010 is 2. So we get the octal. We go to the same number, and we it's as a set of 4, because we are dealing with hex. So we got 0011, 1101, and 0101, and the fraction is 0001 and 101. So we convert to the hex digits. 1010 is equivalent to 10 decimal, which is A. This is B, and this is C. Then we have 1D. Now, case number 3. B1 is equals to 10. This is slightly more difficult than the other cases. It means here we are conversion of decimal to any binary system, which is binary, octal, hex, or entered non-decimal. So here we will take the integer part, or the integral part, and the separately from the fractional part. We take the integer part first, and we'll do repeated division by the base of the number that we are looking to convert to. So to the base 2, in other words. So in this case, the integer we are looking for dn minus 1, 0, base 2. These are evaluated by repeated division as follows. We divide the integer of the decimal number by b2. So we'll take the integral part of n divided by b2 will give me a quotient and a remainder, q0 and r0. q0 is the first quotient and r0 is the first remainder. The remainder will be d0. The remainder, r0, will be equal to d0, which is the least significant bit of the number that we are looking for. Now, to find d1, we will take q0 and we divide it by the base b2. And this will give me q1 and r1, where r1 will be d1, and we take q1 and divide it by the base b2 again, and until we end up with no more division, or we end up with 0. So the process will be terminated. So the remaining d's are evaluated by repeated divisions until the last quotient is 0. Last quotient is 0. Once we have the last quotient is 0, the last remainder will be the most significant bit of the number that we are looking for, base 2 of base b2. Now, for the fraction, take the fraction of base 10, and we need to get d1 minus 1, d minus 2, until d minus m to the base b2. To find d minus 1, we multiply the fraction by b2, by the base of the number that we are seeking. The integer part of the product is equal to d minus 1, and the fraction will multiply it again by b2. So this is multiplication. The fraction, to get the fraction, is multiplication. So once actually we multiply once we multiply, so we multiply with the base. So initially we multiplied by the base. To get d minus 1, we will take the decimal fraction as a whole, we multiply it by b2, and this will give me I0 of 0. D minus 1 will be I0 will be the integer, and we take the fraction f0, we multiply it again by b2, will give me I1 f1. D minus 2 will be the integer I1, and f1, we'll take it again and we'll multiply it by b2, and the process will continue, and you may not end up with 0. If you don't end up with 0, it means you have a repeated fractional sequence, and we'll see an example of this. Now, as an example, we would like to convert 12.75 decimal to binary. So we'll take the 12, the integer we divided by 2, which is the base of the binary number that we seek. You will get 6 plus 0. Since we have a remainder of 0, d0 will be equals to 0. Take the 6, the integer. This is basically I0. So we'll take the integer, which is 6, we divided by 2, we'll get 3 plus 0. Again, the remainder is 0, therefore equals to 0. We take 3 divided by 2, we'll get 1, and the remainder is 1, therefore d2 is 1. We are not finished yet. We will take the 1 divided by 2, you will get 0, the process will terminate, and the remainder is 1, and the remainder is 1, therefore d3 is 1. So the process will terminate since the last quotient is 0. Therefore, 1, 2 decimal equals to 1, 0, 0 binary. For the fractional part, is 0.75, we'll take 0.75 multiplied by the base 2, so we'll get 1.5. So the integer d minus 1 will be equal to 1. And we take the 0.5 multiplied by 2 will get 1.0. So d minus 2 is equals to 0. The process terminates. Why the process? Because the remainder, the fraction, partial product here, which is 1.0, the fraction terminates since the fractional part of I of 1.0 is 0, which is the process will terminate. So once you end up with fraction 0 of any product, the process will terminate. Thus, 0.75 is 0.11 binary. Well, we will combine now the integer with the fraction, so 12.75 will be 1100.11. Very easy. Now we have another example. We have 12.65 to the base 7. We would like to convert it to a number of base 4. Now this is quite complicated, and the reason of complication here because it's 7 is not actually a regular number. So we have to remember applying the polynomial in the same way. So we'll convert it first to decimal. To convert it to decimal, so we'll have the 2 has a weight of 7 to the power 0, which is 1, and the 1 will have a weight 7 to the power 1, which is 7. Therefore, the 12.15 will have 1 times 7 plus 2 times 7 to the power 0, a plus 6, which is the fraction, has a weight of 7 to the power minus 1, a plus 5 times 7 to the power minus 2. And we'll end up with the decimal number 9.9 0.9591836. Now, once we have a decimal, we can convert the decimal to base 4 easily by applying the rule. We will take the integer part, which is 9, and we will divide it by the base b2, which is the number we seek, because it's base 4. So 9 divided by 4 will be 2 plus 1. Therefore, the remainder here is 1, and therefore d0 will be equals to 1. We'll take 2 divided by 4, it will get 0, the process will terminate, and the remainder is 2, so d1 will be 2. So therefore, 9 decimal will be equivalent to t1 to the base 4, 2 1 to the base 4, 2 1 to the base 4. And easily we can verify the result. 21 is equal to 1 plus 2 times 4, because the weight of 1 is 4 to the power 0, the weight of 2 is 4 to the power 1, so this will be equal to 2 times 4 plus 1, which is equal to 9. Now, for the fractional part, we will take the fraction of the decimal number, which is 0.9591836, and we'll multiply it by the base b2, the number we seek, we are looking for. So we multiply it by 4, we'll end up with 3.8367344. Therefore, d minus 1, significant bit of the fraction will be equals to 3, which is the integer. We take the fraction, we multiply it again by 4, and we get also 3 for d minus 2. You will get 1. Take the fraction, multiply it by 4, and so on and so forth. This process is not going to end. So we can stop at 5 digits. It's quite enough approximation. So we get 0.9591836 will be 0.33112. Then we put dots to indicate that the process has not been terminated. Therefore, at 12.657, that's the number, integer and a fraction, be equal to 21.33112 to the base 4. Number systems complements. For each number of any number system, there are two related numbers of great importance because we will use them in binary arithmetic. These are the b's complement and the b minus 1's complement. The b is the radix or the base of the number system. For binary number system, we have the 2's complement and the 1's complement. For decimal, we have the 10's complement, 9's complement, and so on and so forth. Now, how we define those complements? The complement C1 is defined by 2 to the power n minus 1 minus capital N. Capital N is the number value, binary, and the small n is the number of bits in the number. It's 8 or 16 and so on and so forth. C2 is defined by 2 to the power small n minus capital N. Therefore, C2, which is the 2's complement, equal to C1 plus 1. How we obtain the 1's complement directly from the number? From any given number, the 1's complement of n is obtained directly by complementing each bit of n. So the 0 will become 1, the 1 becomes 0. And this would be equivalent to this equation, which is 2 to the small n minus 1 between parentheses minus capital N. So this will be equivalent to this equation precisely. Every bit of n, we will get basically the 1's complement. Now, the 2's complement, we have two methods. The first method is just we add 1 to the 1's complement. We have the 1's complement, we add 1. Well, directly we can apply method number 2, beginning from the left, the least significant bit to the most significant bit of the number n. We copy all 0 bits. If we encounter with 0, 1 0 or successive 0, we copy them down. Once we hit the first one, then we will copy the 1, and every bit after the 1, and every bit thereafter, we will complement it. So here the rule is quite simple. Beginning from the least significant to the most significant, we copy all 0 bits, 1 or if any, consecutive if any, and the first 1 bit, then complement each bit after the first 1 bit until the most significant bit of n. Now the question, if there is no zeros, the first bit is 1. Copy this one, there is no zeros, we ignore the zeros, there's no zeros. And we complement every bit after the first one. So if the least significant was 1, copy the 1, and we complement every bit after the 1 till we reach the most significant bit, and we complement the most significant bit as well. So we complement every bit, including the last bit, which is the most significant. As an example, we would like to find the ones complement and the twos complement of the binary number n11001101. So C1, by complementing every bit, 1 will become 0, 0 will become 1, and so on and so forth. We'll end up with 0, 0, 1, 1, 0, 0, 1. If we add 1, the 1 will be added to the least significant bit. So 0 plus 1 will be 1, and we'll end up with 1, 1, 0, 0, 1, 1, 0, 0. Now, in method 2, we will look at this number. We will copy the first one, and we'll complement every bit. So this is 1, then we'll get, starting with the least significant bit, you will get 1, 1, 0, 0, 1, 1, 0, 0, which is the same answer here using method 2. I thank you very much. Please subscribe. I will see you very soon. Sincerely, Dr. Hassan. Thank you.